Let's discuss recurrency. When is the renewal chain recurrent? In other words, we're being asked, what are the conditions on the parameters qx, other than the fact that they have to be non-negative and sum to 1? What are the conditions such that the chain is recurrent? And we'll see that it really pays sometimes to consider an equivalent but negated problem and ask, well, what are the conditions that violate recurrency? And so we'll see that works well here, and I suggest you kind of try that if you're stuck with any particular problem of this type. When you're looking for conditions for something to be true, just ask, well, what are the conditions that violate the thing that I'm trying to show, and that's sometimes helpful. So let's start by first just very briefly reviewing again the definition of recurrency. You have a state x, I'm reading here, called a recurrent if rho x is equal to 1, meaning the probability of a finite return time is equal to 1. So we return in finite time with probability 1. Again, we call this hitting time tx, the first time at which the chain enters state x. And then here we've set up the starting point of the chain in state little x, and we're looking at the probability that this time is finite. So we're about to see a clear sort of application-driven example of an infinite random variable, not like a big kind of construction that I've made here with random variable y. And hopefully you're going to start getting familiar with, just more comfortable with the concept of infinite valued random variables. And so, to come back to all the definitions, if rho x is obviously less than 1, we call the state transient, and then we call the entire chain recurrent if every single state in it is recurrent. And so, unless otherwise mentioned, when asked for recurrency, you assume that it's with respect to the state space, and so we're being asked here in some sense to verify the recurrency of the state corresponding to every natural number. So now, I mentioned that it's going to pay here to consider the sort of the negated problem and ask, what are the conditions that violate recurrency? And I'm going to first suggest to you that recurrency here, and even in general, must have something to do with irreducibility. If you're having trouble getting around your state space, and I'm talking about from the Markov chain perspective, if the Markov chain is having a difficult time kind of getting from one state to another, then clearly this must have some impact on recurrency. And for this particular example, I'm going to make the claim that if the renewal chain is not irreducible, then it's not recurrent. So first of all, this is not true in general, and I'd ask you to kind of think through an example where this is not true. But I'm going to try to argue that in this specific example, meaning in the setting of a renewal chain, this claim is in fact holds. So how do we argue this? Well, first we have to revisit the definition for irreducibility. So we concluded in the last clip that the renewal chain is irreducible when every single capital Qx is strictly greater than 0. This Qx was the probability of moving past state x from 0. And now what I'm saying is I'm going to try to assume that irreducibility is broken, right? It does not hold. That means there's maybe some integer n such that Qn is equal to 0. And so I'm thinking of a state n, and its capital Qn is 0, meaning you can't transition to it from 0. You can't transition to any other state past n from 0. So you can't transition to n plus 1, n plus 2, and so on. From 0, meaning can't get there from 0. And this supposedly breaks recurrency as well. Let's see how this happens. Suppose I start off with some state out here. Maybe it's even n. That's fine. What happens? We go back to 0 in deterministically in steps. And then you'll notice right away, because Qn, this capital Qn is 0, there's no way to come back to n plus 1, or to any other state. And so clearly I've just demonstrated that the return time to n and of course starting from n is now infinite. And that's a bit of a kind of strange from in English, right? Mathematically it's fine, but in English you don't say that. You don't say the return time is infinite, you say you don't return. But mathematically it means you return in infinite time, so meaning you actually never return. And in terms of this formula here, it means that rho n would in fact be 0, not just less than 1. It means that there's no coming back at all, right? So it's not just not recurrent. It's really not recurrent. There's no chance at all of coming back. So let's let me see just to regroup here. What did we just show? So we just argued that in the renewal chain example, when irreducibility is broken, so is recurrency. And what does this imply? Well, it immediately tells me that this has to be a prerequisite for recurrency. I must list this as one of the conditions. Maybe there are others, right? Maybe we're going to have more conditions for to conclude that the renewal chain is recurrent, but I must list this, right? So we've just showed that if not irreducible, then not recurrent. Therefore, we must assume irreducibility. We must assume this condition, in other words. This, in fact, is going to have another great consequence, and the great consequence has to do with this list of theorems that you have, and you're welcome to use them in your homework, in whichever way you see fit. Theorem 2.1 is telling us that if x is irreducible, then all states fall into all the states in the state space fall into one bucket, one category. And once you have an irreducible chain, you know that if one of the states is recurrent, then all of them are. And if one of the states is transient, then all of them are. And the recurrent category breaks into two parts as well, positive recurrence and null recurrence, and the same thing applies. Once you have an irreducible chain and you show that one of the states is positive recurrent, they're all going to be positive recurrent. Same thing with null recurrent. With an irreducible chain, if you show one state is null recurrent, all of them are null recurrent. And we already mentioned that being true for transients. So this is a very useful theorem, and we can apply it here, and it essentially means that we don't have to bother verifying recurrency for every single state. That would be very tedious. We have required this already. We have to. That gives us irreducibility, and that essentially tells us, well, look, you can pick the state that you want, verify recurrence for that state, and then by theorem 2.1 that we just looked at, you claim that recurrency holds for all states. And so I'm going to pick state 0 for, sort of, you can try it with others. Maybe I'll make a couple of remarks at the end about other states, but 0 is a very natural state to work with here. Hopefully that's kind of clear. And so the conditions that are relevant for me, the variables that are relevant for me is t naught, the first time that the chain enters a state 0. And notice I've slightly tweaked my definition, not just to show that it can be written differently. It's the same definition. I'm just taking here, before I was taking the minimum over k strictly greater than 0. Here it's minimum over k greater than or equal to 1. They're the same exact definition, just to show you can write it differently with no harm. And the row that I'm concerned about is this one, row 0. Starting at 0, you want the return time to 0 to be finite. We're going to be trying to prove that row 0 is row naught is 1. And let's think about what t0 represents. Really, it represents the number of steps taken in my return trip to state 0. And so we can immediately start trying to write down maybe what's the probability that t naught takes on some finite value k. Notice that I cannot put k equals 0 here for the obvious reason that I cannot return in 0 steps. I have to leave in order to be able to return, and so that's maybe explains this requirement that k be greater than or equal to 1. And and that explains why I'm starting with, I'm considering here only k greater than or equal to 1. And it shouldn't be too hard to convince you that t naught equal to k with probability little qk minus 1. We can try to run an example. What is the what is the number of steps that we return to 0 with? What is the probability that we return to 0 in, say, 3 steps? Well, in 3 steps we can do it like this. We start at 0, we go to 2, then we go take one more step here and one more step here for 3 total number of steps. And you see that that happened with probability q2. And in general, it's true, right? To use k steps in my round trip, I would take 1 step to k minus 1 and wasting 1, and then I have k minus 1 more steps to go back to 0. So that explains the difference in the index here between k and k minus 1. So you can run another example to convince yourself of that, but that's the general pattern that we see. So the next thing I want to point out is the fact that if I sum both sides of this condition here, and I'm summing here over all integers, and there's a reason for writing it this way, I'll mention it in a second, but I'm summing over all natural numbers greater than or equal to 1, and it should be clear to you that the right hand side reduces to 1 based on this condition here. So there's again a difference in the subscript. When I sum from k equals 1 up to infinity, not including infinity, so be careful, right? We don't need to include infinity here. When I sum from k equals 1, I'm actually summing from 0 all the way to infinity. And so the sum is equal to 1 by this condition. And notice how, here the sum goes from 0 to literally infinity, and this one I didn't write that. This is a matter of notation. So this really, writing this as a sum from k equals 1 up to infinity, this is really what's meant. What I'm trying to alert you to is the fact that this notation doesn't mean that you ever actually put infinity into the q here. Right? That would be deceptive. And so because we're actually dealing with infinite valued things here, I want to be careful to not place an infinity value here. In fact, what I'm trying to conclude is the opposite. I'm trying to conclude that the number of steps in my return trip to 0 equal to infinity. The probability of this is 0. That's what I'm trying to conclude. Because in the end, my goal is to argue that this probability is 1. Right? The complement of this set is t naught equal to infinity. And if I can conclude that that probability is 0, then clearly this one has probability 1, because the two sets are complements and the probability is at most 1. Let me come back here. So this really, let me just rewrite it. So it's perfectly okay for me to write k equals 1 to infinity here, but I just want you to be kind of wary what that means, right? This is, just symbols, or just notation, but this never means to actually take the infinity and substitute it here. The actual definition for this, if you're kind of interested in sort of the very rigorous take on it, you would write this as k equals 1 up to an integer n, and the infinity represents a limit. So anytime you see an infinity, you're usually thinking of some kind of a limiting operation, and so this symbol here just means take a finite series from 1 to n and then take the limit as n goes to infinity. And this notation is exactly the same thing. It's actually the sum from 0 to n and then taking a limit as n goes to infinity. And so if you actually substitute all of those words, right, for this symbol here, meaning substitute the n and take the limit, you will then obtain this as well, right? The fact that this sum equals 1 because the q's are a distribution and sum to 1 over the natural numbers. So you may ask then, why does this imply this? Well, simply because we've exhausted all possible values for t naught. right? If we're looking for all the values that T naught could possibly take, and we've enumerated them here, and we've exhausted all possibilities because the final sum is equal to 1, and these sets are obviously disjoint. And so, in the end, we have to conclude that T naught actually equaling infinity is impossible, or rather has probability 0. And the fact that T naught is less than infinity is, actually equal to 1. Maybe I can mention one more quick thing. What is this set actually equal to? So this event, T naught less than infinity, how could you write it in terms of these events? Well, it's the union of these, right? These are disjoint sets, and if I take the union of overall possible k from one, from, I would say, k in the natural numbers with k greater than or equal to 1, that's what this event is, right? So the event that T naught is less than infinity is actually the union over events of the form T naught is equal to k over all natural numbers greater than 1. So we've just argued that the state 0 is in fact recurrent, and because the chain is irreducible, all states are recurrent, and so no extra conditions are needed besides this one to argue for the recurrence of the renewal chain. This turns out to be the answer. And then obviously, as soon as this is violated, the chain is not recurrent, and you have then you must then have transient states. Notice you can't claim that the entire chain is then transient, so be careful. So let me put up the definition again. When a state X is recurrent and otherwise it is transient, so that part is true, but be careful not to make the mistake that just because there is a state that's not recurrent doesn't mean that all of the states are going to be transient. And the reason is that we've broken irreducibility here. So just one more time to review, what allows us to conclude recurrency for all states after showing recurrency for just one state is irreducibility. As soon as here I claim that some state is not recurrent, I also lose irreducibility, and therefore I cannot claim the entire chain is transient. So as soon as this condition is violated, there will be some transient states and there will be some recurrent states, and I cannot call the chain either transient or recurrent. But as soon as the chain is irreducible, then once again you show the property, some property for one state, and you conclude it for all the other states. So this is a really nice property of irreducibility, again in this theorem. As soon as you show irreducibility over the state space, then all the states fall into one of these bins: positive recurrent, positive recurrent, null recurrent, or transient. And so positive recurrent or null recurrent, those are just types of recurrent states. And so in the next clip we can actually break down this recurrency into showing what conditions for Q will lead to a positive recurrency or a null recurrency.